we go. All right. So today we will be talking about recursion, continuing the ideas we introduced in lecture on Tuesday. And if you're looking for today's slides, you can find a link to them in the Course.Care discussion. I'll also have them posted to the course website later today. Apologies for the coughing in the last video. You'll still hear some lingering elements there. I'm pretty sure I got COVID at the Final Four viewing at the Dean Dome or on Franklin Street, jumping over a fire afterwards. One of the two led to my demise, but I've been testing negative for over the past week. Unfortunately, still have a slight lingering cough. A couple of quick announcements before we get into today's diagrams. The last reading of the semester is due tomorrow. So I think most of the classes turn this in based on submission numbers, but if you have yet to do this, I would try and knock this out tomorrow. It's a pretty quick read. The last exercise of the semester is due on LDoc. It's on recursion. It was posted on Tuesday. The last day to hand in late is a little bit different on this one because we just don't have time to be able to have a late hand in that goes a week after. So the last day to hand in late is Saturday, and we can't accept anything late on exercise 10 after that, unfortunately. I will note something that I mentioned to the previous section. This isn't in the syllabus. We don't like to advertise this until the end, and I wouldn't encourage you to lean on this for this particular exercise. This is very valuable practice for the final. But if for some reason you get caught in a pinch, we do drop the lowest exercise of the semester in the worst case. So that'll apply to everybody. So if this one, you can't get to full credit on it by Saturday 4:30, I wouldn't be overly stressed. However, as I mentioned, this is really good practice. You're going to see recursion on the final, and the only way to get comfortable with it is to practice it, and these 5 functions that you have to implement are, I think, really great ways of learning it. Today's lessons include a couple of functions which will help you with this exercise, and I'll talk about that at the end, as well as Tuesdays. After today, you should be able to knock exercise 10 out, no problem. And the other thing to note is last day of office hours is on LDoc on Wednesday, and we'll close at 5, so that the TAs can celebrate LDoc the same way that I hope you all celebrate LDoc in the undergraduate library. And we'll have a review session, though, on Thursday. I'll lead this up. It'll be live streamed. There's some things that I'm still waiting to have scheduled on Thursday. So this will probably just be in the evening sometime. I'll post an official time and make an announcement of it. This will be recorded, and it will be primarily Q&A based. I won't have a ton prepared, so I think these things are more interesting when questions are brought. The final is Saturday, April 30th at 8 a.m., so a week and a half away. Your section is special because you won't be taking in this classroom. You're going to be hearing reminders about this from me, and when I assign seats, you'll see that you're assigned a seat not in Hamilton 100, but in Genome G100. Because we have a common hour exam, that means both sections will be taking at the same time. Section 1 will be in here, and you all will be in Genome, which is actually a cushier, more plush environment to take and examine, but they're very similar classrooms otherwise. As a reminder, because this is a common exam, it's scheduled at the same time as another class period's exams. I forget exactly which. I think it's like Tuesday at 8 a.m. or Monday at 8 a.m. If you have 8 a.m. classes, check to be sure you don't have a conflict. If you do, just register that with the registrar. You go to their site, and there's a form that you fill out. I think most of you have done this at this point. Same with 3 and 24 hours. And the alternate time is Sunday, May 1st, so the day after at 8 a.m. in Sitterson Hall. And the reason for this is we just need to knock the grading out of this, the grading out on this as quickly as we can in order to turn grades around as fast as we can. We try to hit the 72-hour mark. There are some semesters where just because of the size of the class, that's a little bit infeasible for us to pull off, but that's my goal, is to get grades out within 72 hours of Saturday. I think those are all the announcements, so we're going to jump right into our first diagram here. And this diagram involves recursion. I would encourage you to try and identify the base case and the recursive case. This is a challenging question. This will warp your mind a little bit. But let's spend another 10 to 15 minutes trying to work through this one and work through it carefully. All right, so hopefully some of the fundamentals of a diagram like this are feeling pretty comfortable at this point, where we've got a globals frame. The only thing in globals is this reference to our function. Nothing important there. And then we see on line 13 the function call that kicks this recursive process off. And it's just I want to just remind you, when it comes to recursion, there's really nothing special about it that's different from what you already know about function calls, other than it feels a little bit strange at first to be calling a function from within itself. But as long as you remember all the steps that apply to any other type of function call we've done, you should be just fine. So this is just a plain old function call. We set up our parameters, start and end, are 1 and 3, and the return address is line 13. So we jump in, and we're on line 4. And I'm going to change colors here so that this is a little bit more visible, right? So we're on line 4, and we set up this variable s. All right, so s is a string variable, and it's initially the start of our current frame. So our current frame is the lowest frame on our stack that is yet to return. It's this one here. And our start in this frame is 1, so this is the string 1, followed by a space. All right? So we've set up s in this frame. We then reach this conditional. And this conditional is where we have both of our base case and our recursive case effectively being specified. Our base case is when start is greater than or equal to end. That's not true in this case, right? Start is 1, end is 3. So we would go to the else branch. And the else branch is where we see this is the recursive case. And this is where the recursive function call happens. We know this because we see a function call to the function stairs that's calling itself from within itself. But notice that we are changing one of the arguments that we're calling this with. Start is not going to be the same. It's going to be 1 more. It's going to be 2 than our current start. And end will be the same. It will also be 3. I want to point out that we need to go figure out what is the result of this recursive call. And when we're done with that, that's when we're going to concatenate it onto the end of s, right? So we can't concatenate anything onto the end of s right now. We need to go process this recursive call, and then whatever it returns, we're going to add that on to the end of our string s in this current frame. All right, so we set up another frame. And the next frame is also to the function stairs. And the return address this time around is line 8, right? This is where this function call is encountered on line 8. And the start this time is not 1, but what we just saw is this argument is evaluated to 2. So start will be 2, and end will still be 3, right? And the reason for end being 3 is we look in our current frame when this function call was encountered, end was 3 there, so it's going to be 3 in the argument we pass along. And now that we've established our frame, we're ready to jump into it, right? And so now our current frame changes. Our current frame is this one. We've established our parameters and our return address, and we start our evaluation of stairs fresh. It's a brand new call, but now our current frame is yet again the lowest frame on the stack that's yet to return. So it's this second frame that we're now working on where start is 2 and end is 3. So what do we do? Well, we reach line 4 again, and we set up s within this frame to be the string start concatenated with the empty string. So it's 2 followed by a space, right? So start in the current frame is 2, and so that's what leads to s being set up as 2 followed by a space. And then we reach our test here. Is start greater than or equal to end? Start is 2, end is 3. That's false. So we go to the else. And once again, we reach this recursive case where we've got another call to the stairs function that we need to evaluate. Whatever it returns, we're ultimately going to concatenate to s. But we need to go figure out what does this function call actually evaluate to. So we set up another frame for stairs. when we set up our start and our end parameters, we need to figure out, well, what is start plus 1? In the frame we're coming from, start was 2, so start is going to be 3 in the next frame, and end is also going to be 3, and the return address was line 8, right? So that's where this function call originated. All right? So now our current frame is this frame, right? It's the lowest frame on our stack that is yet to return, and we've just set it up, so the next step is to jump to the top of this frame, or top of this function definition, and set up s, right? So we set up another variable s locally. This time around, we're concatenating start. Well, in the current frame that we're working in, start is 3 with the empty string. And then we reach this conditional where we're testing, is start greater than or equal to end? And in this case, in this frame, that's finally true, right? We've reached our base case. And what do? Well, so we go into the then block, and we concatenate turn to s. So s in our current frame is no longer just 3. It's 3 followed by turn. All right? We skip over the else. All right? That was our, because start was greater than or equal to end, we carried out line 6, and then we skipped the else. And now on line 9, we are once again concatenating to the string s plus equal, the current value of start. Current value in the frame that we're working in is frame 3, or is 3. Okay, so it's 3 turn 3. And then finally we hit this return statement on line 10. So our return value here, I'm going to write this kind of small, but it's just the string 3 turn 3. All right. Now, I'm going to circle or square this statement and draw my bookmark as right here to say that what we're about to do is we need to go finish up. We're not done with this yet, right? We still have more work to do to complete this code listing, but we've reached the bottom of our recursive process, right? So we finally reached this base case where we're not calling stairs recursively anymore. We finally have a return value for our last recursive call. And now we're about to send that value back to the previous frame for it to complete its work. Before I do that, are there questions on how we got to this point? We're not done yet. All right? So we've reached line 10. We've entered our return value for this frame that we're working in. And the frame that's our current frame is no longer this one, right? We're done with this frame. Its job is done. So we're moving back to this frame. And the way that we move back to a frame with a return value, right, is we take that return value and we send it to the return address. So the return address was line 8. So this call to stairs effectively evaluates to 3 turn 3. Right? That was the return value from the frame we were coming from. So this string is 3 turn 3, but now we're working in this frame, right, that hasn't yet returned. So we still need to complete line 8. Line 8 is saying, take that return value, 3 turn 3, and concatenate it to s in the current frame. So now s is going to be 2 followed by 3 turn 3 here. And we've completed line 8. So then we reach line 9. And on line 9, we're going to say in the current frame, take the current value of s and concatenate start as a string to it. Well, start is 2 in this frame. So notice we're saying, 2 is appended on to this string. And then we're about to process line 10 here. Before I process line 10, any questions on those steps that we just took? So there's this question of why did we skip line 9 the first 2 times around? And this is a great question. What I want to point out is that the first 2 times, we didn't actually skip line 9. What we did was we paused, and we said, we need to go figure out what is this function call going to evaluate to. And that took calling stairs twice. That's how we had 2 frames here. And what just happened is when we reached our base case where we evaluated line 6 and there were no more recursive calls, and we returned 3 turn 3 back to line 8, right? We finished out what we just did in this current frame that we're working in was we finished out this line, and then we resumed to line 9 in this frame, right? But when you reach a function call, you have to go completely figure out what's the complete evaluation of that function call before you can come back and complete the rest of the function body. So we're going to reach line 9 in our very first frame as well, and we'll have run line 9 3 times, but we're not quite there yet. So we just finished line 9 in the current frame, so now we have 2 3 turn 3 2 as our string, and we reach line 10 in this frame that we're currently working in, the lowest frame that's yet to return. So our return value here is s, which is the string 2 3 turn 2, 2 3 turn 3 2, and we're returning that back to line 8, right? So this frame has completed, and we're returning that string back to line 8, the line that we were previously working on in the top frame, and this function call evaluates to that string that we just returned, right? So 2 3 turn 3 2. Right? So to complete line 8, what we need to do is concatenate that to s in our current frame, right? So s plus equals 2 3 turn 3 2, and our current frame is the lowest one that hasn't returned, so that's this very top frame for stairs. And so now s is going to be 1 2 3 turn 3 2, right? And we're done with line 8. So then we continue on to line 9. So we didn't skip line 9. We're just now finally reaching it in this very first top frame that we're still working in. And we add on start in the current frame. So start in the current frame is 1. So we concatenate that onto the end of this string, followed by the empty string, right? And now finally we reach the return statement of our very first call to stairs. So our return value here is whatever s was in this frame. So s was 1 2 3 turn 3 2 1. And we return that back to line 13. So line 13 was in globals, and so this call to stairs with the arguments 1 and 3 ultimately results in the string 1 2 3 turn 3 2 1, and that's what's going to get printed out as output, right? So this is our output for this particular example: 1 2 3 turn 3 2 1. And so what we're seeing in a recursive function that gets evaluated in this way is we reach the recursive case, we set up a new frame, we go into it. We reach the recursive case, we set up a new frame, we go into it. We finally reach the base case, and we start working our way back up. It's a lot like when you enter a building, and that's kind of what this was alluding to. If you start, let's say the building has 3 floors below ground, you start at floor 0, and you walk down to the next floor below you, you walk down to the next floor below it. If you want to get back to where you came from, you have to go back to those floors that existed between where you started at and where you ended at. And the same is true with any function call, right? Whenever one function calls another, if that other function called another function, you first finish the very last function call, you come back to where you came from, you come back to where you came from. It just so happens that what's special about recursion is you're jumping back to, or you're jumping into the same function as itself. This is why we keep track of return addresses, though, and have diagrams that keep track of every frame on our stack, because if you didn't do this, one of these types of problems would be very difficult to work on. Other questions on this example? So there's one question: why did we concatenate 2 on the end here and another 1 on the end here? Those last concatenations for each of those, and actually 3 on the last one, are line 9. So line 9 happens after the recursion has completed. So after this recursive call completes, that's when you can finally concatenate on the end what the current value of start is. And so you'll notice that in each of our frames, we're like the very last value, or string in S was the same as its start parameter. There's another question about spaces. on an actual final, or on the final, if you see a question like this, we wouldn't have like a string that grows really long like this. We would probably be using numbers because they're just a little bit more straightforward to deal with, and then you don't have these space issues. But if you wanted to show that there's an extra space at the end, that's fine. Any questions from in the classroom on this one? All right. On this second diagram, we're going to be working with a linked list. And in this diagram, I'm going to caveat that we're not going to diagram the constructor. So I'm going to help you set this one up. And effectively what I'm going to do is just give you what L is in global. I'm going to do this on this. I'm going to make this small for a second, and then I'll come back to the larger size when we get there, or for you all to work through it, because I know this really small font. So globals has a node class on lines 4 through 10, and a find function. So those are two names we define. Find is on 13 through 23. All right. And then we reach line 26, where we set up this variable named L. And L is being assigned, and here's where you see we're constructing a list of nodes, but we're doing this in a nested way. And you'll see this on the current exercise, where because of the way this constructor is set up, the second parameter of the constructor is you can give us the next item of the list. So when we construct a node or a list in this way, we're going to have a node with data 1 that's followed by a node with data 2 that's followed by a node with data 3 that's followed by none, or the empty list. So I think for the purposes of an example like this, tracing out each of those constructor calls is something we did a lot of in the last unit. So I'm going to caveat that we don't need to, if we give you the instructions on a question and say you don't need to diagram a constructor, it's totally up to you. In general, once you're comfortable with this idea, hopefully this feels much faster, where we can just say, okay, our first node has the data of 1, and a next that is going to be a node that comes after it. And the next node that comes after it is another node with a data of 2. And a next node that comes after it. And the final node in this list with 3 elements in it is a node whose data is 3. And make that a little bit clear. Has a next that is none. All right. So I think what I'm going to do is help you set up this very first frame for find as well. And then I'm going to leave it on this slide, but if this slide has too small of text for you, in the discussion, towards the top of the discussion, there is a link to today's slides if you want to be able to see it in full size on your screen. So on line 27, we're trying to print the result of calling find with L, which is the reference to this data with node 1, and 4 as the second argument. So I'm going to work through setting up this frame with you, and then I'm going to turn it over to you. So find was called on line 27. And the head parameter is assigned a reference to node whose data is 1. And the needle parameter, we're trying to find a needle in a haystack here, is the value 4. All right, so that'll set that frame up. And I'll turn it over to you all to take it home from here. All right, let's work through this together. So we've just set up this frame for find. Again, this call happened on line 27. And we set up our parameters. Notice we called find with an argument of L. L in globals referred to the node whose data was 1. So head, the parameter that we're passing that argument to, is also going to refer to that same node. And needle is 4, the second argument. So our current frame is this one. It's the lowest frame that hasn't returned. And we jump in. And we test is head none, or head is none. I mentioned this in the video on Tuesday. I think when you're testing for none, this is the more idiomatic Python way of doing it. So I would encourage you to get comfortable with this concept. When you use the is keyword, you're looking for if something is exactly, which is a little bit beyond our concern right here. But when you're testing for something being none, it's more common to use is than the equal sign, although either work just fine. So head is not none, right? Head is a reference to a node whose data is 1, so that's false. We skip past it. We then go to test if head.data is equal to needle. So we look, remember when we see the dot, we're following the arrow. So head dot follows the arrow to data. Data's value is 1, needle's value is 4, so these are not equal to one another. So we once again jump to the else, and we see an if statement. If head.next is none, head.next is not none. It's a reference to another node. So this case is also false. And finally, we reach this case where we're going to return a function call. But before we know what we can return, and the reason why we're not going to enter an RV into this frame quite yet, is we don't know what the return, we don't know what value we're returning. We need to go figure out what is this function call's return value going to be first. So we need to set up this frame. This is another call. This is our recursive case. This is where recursion happens in this example. And so we set up our frame. So our find frame is going to have a head parameter. That is whatever head.next was in the frame that we're coming from. So head.next was a reference to the node whose data is 2. So this head parameter is going to be a reference to that same node. And then needle in the frame that we're coming from was frame 4. So needle is going to be 4 as well. We didn't change it at all. And our return address is line 23. All right? Once we've established our frame, we know we're going to have to come back to this point, but we need to go figure out what does this function call evaluate to. So our current frame changes to become this frame. It's the lowest that hasn't returned. And we go all the way back up to the top of the function, and we're starting a brand new function call into the find function. But notice that our parameters are a little bit different this time around. Head points to a different node, the next node in our list. So we test again. But this time around, we're working in this frame. Is head none? No. Head is the node whose data is 2. So then we test, is head.data equal to needle? Head.data is 2, needle is 4, so no, that's false as well. And then we test, is head.next none? No, head.next refers to the node whose data is 3, so that's also false. And then finally, we reach this line again, where we have another function call that we need to go evaluate before we know what to return in the current frame. So I'm going to set up a new frame. We're once again calling the find function. And the return address is once again line 23. Our head this time around, when we're setting up these parameters before we get into this frame, is head.next in the frame where the call occurred. So head.next in the frame where the call occurred is a reference to the node whose data is 3. And so now this head is going to refer to that same node. And needle doesn't change, so needle's value is going to be 4. Right, so we're searching for this needle in this haystack. We haven't found it yet. Now that we've established this frame, we've set up our parameters, we've set up our return address, our current frame becomes the one we just set up because it's the lowest to return. And we go back to the very start, brand new function call, ready to start again. But notice this time around, the parameters have changed yet again. Head now refers to the node whose data is 3. So we test, is head none? No, it's this node whose data is 3. Is head.data equal to needle? Needle is 4, head.data is 3, so no, that's still false. Is head.next none? And this time around, notice this is actually true. Head.next is none for the node whose data is 3. So this is the case that we hit, and we finally hit a base case, right? So there are 3 base cases in this function. the first three conditionals, and then the last is our recursive case. But we've hit this base case, and so now we're finally going to enter a return value for one of these frames, right? So our return value is false for the frame that we're working in. And once we hit the return statement of the frame we're working in, we're sending that value back to our return address. So our return address was line 23. So line 23, this call evaluates defaults on line 23. And then once we realize that, we know that, OK, we're moving back to the frame that we just came from. Or we're moving back to the frame that has yet to return, the lowest frame on our stack that is yet to return. Right? So we're moving back to the frame whose head pointed to data of 2. And here we see, oh, this function call that we just evaluated, that returned false. Well, we're in a return statement, so this function frame is also going to return false. We're just going to keep passing false back up. So this return value is also false. Where are we returning this false value to? Well, our return address for the frame we're in was line 23, so that same line, we return false again. But when we return, we're no longer working in that frame. We're now working in the original frame for find, where head referred to the node with data 1. And we need to finish evaluating this line where we just returned to. So return false again. So this will return a value of false. Where are we returning false to? Well, we're returning it back to line 27. Right? So that's why we keep track of the return address. Line 27 occurred here, the find where L was the first node and 4 was the needle. And this results in the output of false. Right? And our program's done. Questions on this example? Let me check chat as well. Not seeing any there. Oh, yep. Yeah. So the question is, why is the return value false for the first frame, and the same logic will apply to the second frame as well. Different logic applies to the third frame. And so I actually want to start there. So if we sort of zoom out just a little bit and think about what this function's doing, and I'm actually going to change colors here to try and highlight this a little bit more obviously. All right. So I want to try talking about this from a slightly more abstract level, and then we'll zoom in to that very specific question. At a slightly more abstract level, this function is saying, hey, go find in this list, that list starting from 1, 2, 3, go see if you can find 4 as one of the data values in this list. That's what this function is implementing. And the first frame is saying, OK, I'm going to check that first node, and I don't see that value. 4 is not 1. So I'm going to use the same function to go check the rest of the list. So when you call that function calls itself the second time, it's saying, hey, see if you can find 4 on the rest of this list. So that function, notice, is just checking the node whose data is 2. 2 is not equal to 4. So then that function says, I didn't find it. I'm going to call this find function again. Go check the rest of the list. So that's what led to this third call to find. This third call to find, we're still looking for 4, but this time around we're checking this third node. And so each of these function calls, we're moving closer and closer to the end of our list. And finally, in this node, we realize there's no next node for me. There's no rest of this list for me to check. And at that point, that's where I'm going to return false. So to get more specific, in this last, when we were working on this last frame here, that's when we reached this case, right? And that case is where we very explicitly returned false. And that's why we entered a return value of false there. When we returned that, we returned it back to this, the previous function call to find, and this particular line, right? So on this particular line, from this frame, head.next was a reference to this very last node, and needle was still going to be 4. And the result of calling find on that was false. And so this function is ultimately, or this return statement simplifies down to return false, right? And so it's that recursive call that led to, return value false being entered into this frame and that frame completing. Well, where this is kind of tricky and confusing when you first encounter it is, well, we still need to sort of say back to the first frame, find, hey, we didn't find this in the list that came after it. So this also evaluates defaults in the frame, in the very first frame, because we didn't find it anywhere after us in the list, and then we're going to return that back to where we came from. So in a sense, what this algorithm is kind of doing is, Chelsea and Megan, come up here for a second. I'm going to give you an example of what this algorithm is doing. So imagine I'm the first node in this list, and we're calling find, and we're looking for Chuck Norris in this list, right? I'm going to put one hand on you, you put one hand on Chelsea, you put one hand into the ether, you're pointing to none, right? So this very first frame to find, I'm saying, you know, are you Chuck, am I Chuck Norris? No. Are you Chuck Norris?
No. Are you Chuck Norris? No.
And then pass it back up.
Oh, no.
No, right? And so these three function calls that are happening are kind of working down the list and then working their way back up. And it's that passing defaults back up to the first node in the first function that called it that's kind of leading to that. Thank you all. And we could have seen if we did this with, if we had asked, if I had said, you know, am I Chelsea, or is Chelsea in this list, we could have gotten to the end. Chelsea would have returned true if had that data had been equal to needle, and that would have been passed back up, true, 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 to the original caller. So that's the intuition of this example. Other questions on this one? All right. And I just realized, sorry, I didn't have the classroom camera on for the folks who are on Zoom. We were just touching shoulders. So in this last diagram, let me check questions online one more time. Nothing there. OK. In this last example, I'm changing this node to be a little bit different. And what we're going to be doing in this function is building up a linked list. And this time around, notice there's no constructor here. So when you reach line 14, in your current frame, what I just want you to do is set up, you know, n to be a node whose data is initially -1, because we're specifying that as the default value, and whose next is none by default. So once again, we also don't need to add constructor frames in this example. When you reach line 14, you're just going to set up n to be a reference to a brand new node in the current frame that you're working in. All right, so that's not the diagram. Was sort of just giving you a sense of what happens when you reach this line. As you get there, you're going to be doing something that looks like this, just to set up that node in memory. So go ahead and try diagramming this. You've got a class node, a function build, and then this program kicks off really on line 20 when we call the build function and you set up a frame for it. All right, let's work through this together. So we've got our line set up. I went ahead and carved out some space in my globals for head, which is going to be a reference to either to none. It's either going to be none or a reference to a node. And it's going to be assigned the result of calling this function. But we don't know what the result of that function is because we haven't processed it yet. So we need to set up a frame for it. So we set up our frame for build. And it has two parameters, start and end. And our return address is line 20. All right, so on line 20, we called build with a start of 0. That's the first argument, and an end of 2, which is the second parameter passed from the argument value 2. We've established our frame, so we jump into the top of the function, right? And this is the rule that you're always playing out. You set up your frame, and then you jump into it. And as soon as you jump into it, the current frame that you're working in whose values you care about, is the last one that hasn't returned, the one that you just set up. And we test, is start greater than or equal to end? No, 0 is not greater than or equal to 2, so we go into this else branch. And notice, you can already tell this is a base case, and we already know this is a recursive case because that's where the recursive function call is occurring. But we haven't gotten there yet, so on line 14, we set up n. And here's where I was saying, because there's no constructor defined, we can set up an object with the default values. So I'm going to set up node with a data of -1 initially, and a next of none. All right? Those values came from the defaults in the class attributes, right? So our class attributes can have default values. Data is -1 by default, and next is none. Right? On line 15, we see that we're changing n.data. So n.data is no longer -1. It's now going to be start, which was 0 in our current frame. Right? So start in our current frame is 0. And then we see n.next is going to be reassigned to whatever the result of calling build is. So this is our recursive call. We don't know what this recursive call is going to do, so we need to go evaluate that function call. And then once we have a return value from that frame, which will be the next frame we set up, then we can say n.next is that returned value. So we reach this function call. We need to set up a new frame. So we're in the process of setting up our frame. We're calling the function build. The return address is line 16, right? And we need to figure out what are our arguments. Well, before we actually jump into that frame, while we're still setting it up, our current frame is still the one that this call occurred in. So start was 0, 0 plus 1 is going to be 1, and end was 2, so end is also going to be 2. We didn't change that. So when we set up this frame, start will be 1, and end will be 2. All right? Now that we've established the frame, we're ready to jump into it. So when we jump into a function call, we go to the very top. But now our current frame is this one, right? So we're working in this frame. And we reach the very first statement again. If start is greater than or equal to n. 1 is not greater than or equal to 2. So we once again go down to this case. And in this case, we set up a variable named n. And it refers to a new node. So we set up a new node. And that node has a data initially of -1 and a next of none. Right? Because those are our default values for those attributes. And then we reach the line that says n.data is assigned start. And here's where you have to be careful, right? We need to know what is our current frame. Well, it's the one that has yet to return that's the lowest on our stack. And start in this frame is 1. So we're saying 1 is assigned to n.data. And n is this frame where data is currently -1, so data here is going to be 1, right? So we've completed line 15. And then we reach line 16. n.next is assigned the result of calling this build function again, but with different arguments this time. So we need to set up a new frame for this call to build. So the build frame, return address is line 16. Start, this time around is 2, right? Because in the frame we're coming from, start was 1. 1 plus 1 is 2. So start will be 2. And will still be 2. And now that we've established this frame for this call to build, we change frames. We go into this frame, and we go we start a new function call from the top. We go back up to the top. But now our frame has a start value of 2 and an end value of 2. So when we reach this test, if start is greater than or equal to end, in this case, this is our base case, and we return none. So our return value here is none. And that's OK, because we said we can return optionally a node, so returning none here is OK. We're returning none back to line 16, right? So line 16 is this line. This evaluated to none. And when we return, we go back up to the frame that we were previously working in, the one that's yet to return. And here we're seeing n.next is assigned none. This is kind of a silly thing because n is already none. So it seems like we did a lot of work for nothing. We could have rewritten this in some other ways, but effectively we assigned n.next to be none. Well, it's already none. That's OK. We're done here. And when we reach line 17, things get interesting. All right? And this is where the sort of beauty of this particular function comes into play, which is we're returning n in this recursive case. N is a reference to the node whose data is 1, so the return value of this frame that we're just completing, right, is going to be a reference to that node whose data value is 1. Where are we returning that reference to? I'm going to actually change colors for this part because it's so important. We're returning it back to line 16. This is line 16. This was the function call that led to this reference to this function being returned, right? So now, n.next in the frame that we're in our current frame is going to be assigned to that reference. So n.next here is no longer going to be none. It's going to be a reference to the node whose value is 1, all right? And this is the important step to understand in this example, besides how those parameters are changing. Again, when we're in this frame and we reach this return statement, we're returning this reference to n. We're returning it back to line 16, but in the frame that came just before it. And that's what allows us to set up this link between, oh, we just built the node, or the list who has 1 as the start. We're going to return a reference back to that node 1, so that when we go back to the build whose start was 0, we're setting up its node to link to that next node whose value is 1. But we're not done with this frame yet, right? It has no return value, so we need to finish it out. We just finished line 16 in this frame, and now we need to complete line 17. Line 17 in this frame is saying return n. Okay, well, n is a reference to the node whose data is 0, so the return value here is also going to be a reference to the node whose data is 0. And we're returning that back to line 20, right? So line 20, this call to build resulted in a reference to the node whose data was 0. So we're taking that reference and assigning it to head. And so head in globals is also going to be a reference to that node whose data is 0. And so what you're seeing here is an algorithm. If we had changed this to be, build 0 to 50, we would have had 50 recursive function calls that occurred and counted up from 0, 1, 2, 3, 4, all the way up to 49. And they would have all been linked together in a list in this way. Here, we kept the parameters a little bit more constricted, so 0 and 2, and that's why we got back 0, 1 in this particular example. But this is a pattern that allows you to generate, with a recursive function, a list of nodes. And this will wind up being important in the exercise in the last two functions that you have to implement. Any questions on this example? Yep. Yes, this is a great question. The question is it only possible to call a constructor in the way that we did without having let me circle this. So the expression that we're talking about here is this one. Can we construct an object without defining a constructor? Is that only possible if we have default values associated with its attributes? I am going to argue, for the purposes of writing good code, that yes, you should always have, if you don't have a constructor, you should set up your default values for your attributes, always. The programming language would actually let you construct a new object without having defaults, but then it's like, well, what actually are these values? And so if you depended on them, you'd have to either know a lot about the programming language to know what it might default to, or you might be in a place where actually some errors would exist in your program. The way that you avoid that, and having to know all those details of programming languages, and it's very programming language specific, is just to always initialize your attributes of an object. And so either you do that by default values when you declare them, or in the constructor, and there are trade-offs to those two things. But yes, effectively, what I would tell you as the rule of thumb is to always follow that as a best practice. And that's a great question and great observation. So there's a question on chat that is the important part of this question. So I want to come back to this and spend just a moment on it, which is how did this, I'm going to change colors yet again. I'm going to go to red here. How did this reference come to be? Right, this is the important one. And if you tried, I would encourage trying to diagram this question with arguments of 0 and 3 instead, so you can see how this works with extra nodes being generated. But this particular reference is set up, if we go back to this frame of build, where we're starting with 1, you'll notice that its n is a reference to that node. So the function call to build with start of 1, its job was to set up the node whose data was 1. And ultimately, it returned a reference to that. Right? So it returned this reference to this node. And where did it return that to? Well, that call occurred on line 16, but in this frame where we were working with n whose data was 0. And so it's this line where we're saying n.next is the result of calling build with a start of 1 and a 0 of end. Right? So this was build 1, and 2 is the end. And that return value was this frame's return value, which was this reference that allowed us to establish that link to the next node. This is a pattern that you will see in the second two functions that you need to implement in the next exercise. They are different, but this pattern of how you can build up a linked list recursively will play out in those last two examples. And then the first three functions that you're working on are a little bit more like this second diagram that we did earlier, this find function. So as you're working on the final exercise of the semester, if you find yourself getting stuck, you can take some of the general concepts of these two examples and apply them to those specific examples or those specific functions. That's all we got for today. I'll see you back here on Tuesday for the last lecture of the semester in person, and we're in the home stretch.